start recording and make this official. So welcome back, everybody. We have just one class this week because I'm getting on a plane tomorrow morning. So I hope that you can use the time Thursday to maybe watch the video that I posted. So on last Tuesday's class, next to its corresponding handout, I did post a video that I made about the transition between longitudinal models as estimated between multi-level models versus estimated using single-level structural equation models within MPlus and Levon, which are pretty much the two main packages that people use nowadays. So that may be helpful to you for those of you who are trying to transition across the two worlds at the same time, as well as get to know some of the advantages that you can additionally add to your model if you're working within an SEM framework. Speaking of which, for those of you who think, this stuff is so cool, and I wish that I could keep learning more, is anyone thinking that right now? Yeah, the right answer is absolutely, Lisa. Next semester, I'm offering an advanced course. It will meet on Tuesdays and Thursdays at the same time, so I got the 12:30 spot for that course. And it's listed as PSQF 7375. It's a special topics. Mine is section 6. And it's titled, I think, Advanced Longitudinal Models. So my plan is to start basically where this course leaves off. So my intent is to get all the way through models of change, then talk about time invariant predictors, so level 2 predictors, and then next semester would start with level 1 predictors, which turns out to be quite more complicated. The only way really to do them right is to move out of a univariate multi-level framework and into a multivariate multi-level or SEM framework. So we'll talk about time-varying predictors, we'll talk about how to model change in latent variables, so what is known as second-order growth curve analysis or higher-order growth curve analysis, things like curve of factors and factor of curves and that kind of stuff. Hope to get some examples with maybe 3-level data, so longitudinal data of people nested in groups or people who are in time-varying groups. So if kids change classrooms every time they're assessed, that kind of thing. Location scale models is another topic I hope to get to, so predicting differences in variance with its own linear model. And we'll see what else we have time for. My intent is to probably do a combination of a little bit of canned homework, but also more individual data analysis project kind of things, because I expect that class will be a little bit smaller and I'll be able to manage that additional grading interaction workload. So for those of you who are interested, that's happening next semester. Question?
There's a bee over there, so I just noticed it over there.
Okay, attention shoppers, there is a bee where Nathan was sitting. Hopefully the bee will leave. Hey bee, there's pizza on the other side of the room. Highly recommend.
But in terms of the advanced course, is it going to be the same format with lectures and homework examples, or is it going to be more like discussion, collaboration-based stuff?
I don't know yet. I think it's going to be a little bit of both, because I have taken classes when I was a graduate student that were taught as a seminar where we all like read a chapter the night before and then someone stood up and tried to present it to the rest of us. Mm-hmm. And I felt like that was not effective. So it's my job to teach you, but it's your job to take it and run with it. And so something that encourages, it's presentation, but then a chance for you to practice on data that are real and not canned. But also, like at this point, I figure if you get all the way through this class successfully, then you know enough to make the programs run, and I can trust you to get that part right. Whereas at the very beginning, such as homework 2 that you just finished, like just finding the numbers and making sure your code is right is enough of a challenge. Speaking of which, I did update grades this morning, and you should be able to look at your homework 2s and see how you did. If you have any questions about things that you missed or you want to know why you missed it, please send me an email. I can't discuss it in front of everybody yet because not everybody has finished. But you should be able to see green answers and anything you missed in red, followed by what it should have been in green. Okay, so we have then, so I told you about the video. We're here today, and so I have meet on Zoom only for next Tuesday with a question mark because I wasn't sure if this system was going to work. Clearly it is working. So I will take this off and we will meet in person a week from today. Tuesday is our next class. Thursday on the 20th a week from Thursday, we will be on Zoom because we're getting kicked out of this room for comprehensive exams again. So that one's not on me or the technology. And after that, we should be able to meet here as regularly scheduled. Things to do next week. Hang on. You already did this one. Why? I updated this. Grr. You already did this one. You don't have to do it again. What it should say here is, yeah, it's this one. That's the one I'm at. You did this one. This is the week. Sorry, I'm like a ball of nerves at this point. You know how it is when you're getting ready to leave town? Well, compounding that is that I'm not only leaving town, but I'm going to a conference that I am helping run. And I'm going to get everything ready for my parents to come and take care of my kids. So like right now my head is just kind of a mess. So please forgive me if I seem a little erratic, because quite frankly I am. But what I do know is that next week you don't have anything due. So nothing to work on necessarily over the time that I'm gone. And that was quite deliberate. That way I don't have to worry about not getting back to folks as frequently or as soon as I typically would. Okay. Any questions on when we're meeting, what we're doing, logistics, that kind of stuff? Okay, then I will assume that my ramble was sufficiently effective. Moving on. So last time, we started heading into discussion of more options for modeling nonlinear change, and we were going through a handout, I believe, of new example data. So we started looking at example 6a. Does that sound right? Maybe? Mm-hmm. So these data we have seen in example 3b. So we're doing more analyses of the same data. Very briefly, we have 6 occasions of measurement. We're looking at improvement in response time to a speeded task. So the outcome is response time in milliseconds. These happen to be older adults, although that's not really part of the story. And what I have first in terms of the sequence of models, so 6A going all the way up through 6D, these are going to be linear effects of time and then followed by quadratic, random linear, all moving up to random quadratic. So that's what we have for today. Question?
Curious question. Why do we always talk about linear regression in classes but never like polynomial regression or higher degrees?
So the question was, why do we say it's linear regression and not polynomial regression?
Or, yeah, like why don't we cover that?
Why don't we cover that? Oh, because you didn't have that class from me is the answer. Okay. So each instructor has to decide, you know, what they're going to cover and what they're going to punt on. And when I did 6242 and 6243, we had a unit on nonlinear effects of continuous predictors. And we did quadratics and we did piecewise models because I knew this was coming. And I wanted to make the broader point that people do talk about nonlinear change as a way to rationalize taking time as a continuous predictor and fitting slopes besides linear to it, like linear plus quadratic or exponential or other types of functions. But absolutely everything that we're talking about applies more generally to any continuous predictor in any model. Okay. Absolutely. And it's probably more reasonable to think about nonlinear effects of continuous predictors because eventually having more isn't going to help you. So everything kind of eventually peters out, slows down, or hits the ceiling of the measurement. So I think nonlinearity is probably more common than what people would expect. But linear regression also, besides just the idea that you're fitting a linear slope, is sometimes referred to in contrast to logistic regression. So linear sometimes means like your standard general linear model. Mm-hmm. Sometimes it means linear slopes only. Sometimes linear model just means a form of a model where it's slope times variable plus slope times variable. So there's a lot. Yeah, it is. It is absolutely confusing. But unfortunately, the people use the same words to mean different things. So, okay. Any other questions before we jump back into looking at longitudinal models? Okay. And so where I think we were, we did saturated means, right? Did the answer key. Does that sound familiar? Maybe? I feel like we did. So. Mm-hmm. looking for converging evidence here, like that my memory is correct and or that we've covered this in sufficient detail to where I don't need to go through it again. So the logic is I want to know what the model's going to try to do. That's the logic here. If you have balanced data and enough people to estimate this model, this tells you what's up. It tells you what the means are that the fixed effects are going to try to recreate, basically what the trajectory would need to look like in order to go through the means over time. The variance side of the model then tells us what the random effects are going to need to do. So if you see relatively constant variance and covariance over time, that's a sign that a random intercept might be sufficient. If you see changing variances in a particular pattern, that's a sign that a random effect of time is probably going to need to be part of the model. What kind is then an empirical question, but getting a sense of what you're looking at first is never a bad idea. So we fit that model in all of our various programs, and we found that the variances of response time, so that's why these numbers are so big, is because it's response time in milliseconds. These are decreasing over time. The correlations, I don't know if you call them decreasing. They're all pretty high. There's not an obvious pattern here. But the fact that these correlations are so high tells us that person differences are the majority of the story here. So even the correlation between the first and last occasion is 0.8. So a lot of the variability here is going to be because of constant mean differences. Question is, what other kinds of person differences might be lurking in the data? Then we have our fixed effects model. So we have the fixed intercept as one of the occasions. It's session 6 here, and then the pairwise differences. And we get all 5 of these pairwise differences lumped together, gives us our F-test for those. So the test of whether there are any mean differences across the 6 sessions is a lumping together of 5 different contrasts. And as long as the contrasts aren't completely redundant, you can create any 5 and lump them together and it would still work. So F is just a way of testing multiple slopes at the same time, which is useful whenever the multiple slopes go with one idea. So here the main idea is, are there mean differences over time, yes or no? F says, yep, there are. Now it's our job to figure out what the pattern is and how we can create a function that's going to recreate those means. So the means then themselves, I had showed you some pictures of what those are going to look like. So let me review those real quick. This is lecture 6. So on the mean side are 2 baseline models. Saturated means created this black trajectory here. And I think we decided that it looks not quite linear last time, like nonlinear-ish. Looks like one line isn't going to fit it. The empty model is the other baseline that we did, which says there's no change at all. So somewhere between the black line and the red line is where we want to be. Likewise, models for the variance, we can do the same thing. So in this picture, the y-axis is the amount of variability at each occasion. And the unstructured model then gives us what the variance is at each occasion, and we can see that it's declining in this particular pattern. Random intercept model says the variance would be the same. So we're looking for something in between these two. Okay. So we answered these 2 questions before about the saturated model, but just to reiterate. So if I'm estimating a saturated means unstructured model using least squares, what would I call it in that context? If I had, say, a one-way factor of time, and I let all of the occasion variances and covariances be whatever they want, what is that?
Unstructured.
It is unstructured, but I'm looking for a synonym that you would know if you took it from a class that specialized in OLS stuff. Yeah, this is the multivariate MANOVA, multivariate analysis of variance, or multivariate approach to repeated measures analysis of variance. Yes. So why would you do it this way instead?
Complete data.
That's it. That's the reason. So the difference between the models is none. The difference between the estimator is y. So we're using residual maximum likelihood here, which means that we use all of the data that we have. Any occasions that a person has go into the model. What would happen if we did this in least squares instead?
Less isolation.
Listwise deletion?
Listwise deletion, which means that anybody who's missing anything gets dropped. So that's obviously bad for power, but it's also bad from the perspective of inference. So if this were a longitudinal study, say, happening over many, many years, do you think the people that make it to the end are a random subset of the people that we started with? Probably not, right? They're going to be the healthiest or the most able or the most compliant. They're going to differ in some kind of way that's not random. So the goal of this model is to recreate what the means, variances, and covariances would have been had we had complete data. And the assumption that we have to make in doing so is called missing at random. So that means conditionally random given the data that we do have for a person. In contrast, listwise deletion assumes missing completely at random, which is just what it sounds like. So you'll probably get the wrong answers if you're forced to use complete data. Unless you want to limit your inferences to people who made it through all 6 sessions, in which case, okay, fine, but then you just have less power. So this is MANOVA, functionally speaking. And if you stay with me this afternoon, what am I going to call this same model in SEM class?
H1.
It's the H1. Yes, indeed. That's the saturated model. It's the best possible height for my data against which we compare every alternative factor model that we would think of. Okay, good. Any questions? Zoomers, I'm watching you too. Any questions? All right, moving on then. So then we built from the ground up, starting with empty means random intercept. You can do this model regardless of whether you have balanced data, so you can always have this as a choice. Its purpose is more descriptive because we know this isn't going to fit. Like, it'd be very rare that you'd have longitudinal data where there's absolutely no change whatsoever and people just differ in their means. But it provides a baseline with which we can assess improvements in fit from adding stuff. It also provides us with a useful descriptive statistic, intra-class correlation per se. So this model then has 1 residual variance, 1 level 2 random intercept variance. We put those 2 things together and they form the diagonal of the V matrix, the marginal variance covariance matrix. And if I turn that variance covariance matrix into a correlation matrix, then we get that jobby right there. So 0.8173 is our intra-class correlation. So that tells us 81% of the variation in response time is what? Between, let's get all the synonyms going. Level 2. So it's between persons at level 2.
Time variant.
Nope. Invariant. Cross-sectional. This is the variation that you would expect had you measured them once. 80% of the story here is some people are faster than others at this task, on average. Yes?
So this, in this case, time has 0 impact on these correlation values.
That's what the model says.
Okay.
That's what the model says. We know what the actual answer is, though. Time has this kind of impact on the correlation values.
So after controlling for time, this is what it is.
We haven't controlled for time yet.
Okay.
So I'm presenting the 2 baselines in terms of like what the most complex model is, which is only possible if you have balanced data and enough people to estimate it, versus the other side, which is the simplest thing that you can always do.
Okay.
So we're starting up from simple in this case. So this model has nothing to do with time.
Okay.
The only thing it says is, okay, occasions from the same person are probably more related. I'll put that in the model. What is in the model that goes with that idea? Occasions from the same person are more related than occasions from different people. Which of my 3 parameters reflects that idea?
Random intercept?
Yeah, the random intercept. So what the random intercept does is introduce a constant correlation of occasions from the same person. That constant correlation is 0.8173. So that is how the model is handling dependency right now. This model says there's only one reason for dependency. The reason is that some people are faster than others. That reason is built into the model as our level 2 random intercept variance across people. So the assumption then is once I put that in there, all the e's are unrelated with constant variance. That's what the assumption is. So more generally, when people talk about model assumptions, it's whatever your model says you're assuming to be true. This model says there's no change over time, the variance is the same over time, and the correlation is the same over time. That's what it says. That's not probably right, but that's what this model is saying. So we add to it to see if we can do better and match the data more closely. Something I will ask you on your next homework, so preemptive cough cough homework question, can I say that? This number right here, that looks pretty big, right? Like a correlation of 0.8 seems like a large effect size. How would I know if that number is significant?
Likelihood ratio test?
Likelihood ratio test. If it has anything to do with variance and covariance, the answer is likelihood ratio test. Now, between what and what is the next question.
So between the previous model without the random intercept and this new version with the random intercept?
Yeah, the model I didn't fit, but the comparison model would be one without the U in it.
Mm-hmm.
The U, the level 2 random intercept variance that is represented by the U, that is what is creating that correlation. So we take it out, that's equivalent to setting the correlation to be 0. That would be an E-only model. That would be just an empty linear regression model. Now, the reason that I didn't have to fit that alternative model is that every software package will do it for you in this one case. So SAS prints that likelihood ratio test right here, which is anything above E only. Basically, that's what this test tells it. So it changes it according to how complex your model is. But this chi-square is the difference in -2 log likelihood between a model for the variance that has E only versus this one that has U plus E. And a chi-square of 700 or so, yeah, that correlation is significant. In Stata output, that same hypothesis, null model likelihood ratio test, is right underneath the fixed effects, and it says something like test against linear regression or something like that, meaning E only. And in R, I asked for that using our friend Renova, so we're using Elmer in this unit until we can't anymore, and that fits the comparison model and does the likelihood ratio test for you. Okay, questions on any of that? So then adding things one step at a time. Yes, it's tedious, and yes, I will show you a shortcut later, but for now we're adding one thing, each thing a step at a time to see if it helps. So I'm moving then to model 2A, page 5 here, where I'm adding fixed linear time. Why linear? It's a reasonable place to start. So I've incorporated beta 1 into the level 1 model. So note that the variable time has a TI subscript. Any variable that is per occasion gets a TI subscript. What that means is that we're not assuming balanced time. This variable can be whatever occasion each person is measured at, even if nobody else was measured at that occasion. Each person can have their own set of little t's. That beta placeholder then gets its own level 2 equation, and so far all that's in it is gamma 1O, which is the notation for our fixed time slope. So this model is saying, let's see if there's change on average. Let's not see if it varies across people just yet. So then we went through this code. We have time in the model. So this was a popular homework email. What's the difference between time in this example and session?
Time is session -1.
Yes, time starts at 0. And session, or wave, or week, or occasion, I will use various synonyms for my level 1 identifier, starts at 1. So a few folks forgot to center session and in their homework and tried to estimate the model. And they found that everything related to their intercept was off. That's not a coincidence. So the intercept is always what happens at time 0. So if you put a variable in the model that starts at 1, time 0 is then outside the scale of the data. And so that's why it wouldn't match. More generally, if you don't have the correct answer for an intercept, it means something is off with your centering, because the intercept is the expected outcome when all your predictors are 0. So then we add that fixed time slope, and it shows up in our solution for fixed effects. And because it's a fixed effect, we don't have to do likelihood ratio test. Just stare at the p-value for the wald test that goes with it. And in this case, could we have done a likelihood ratio test instead?
If you are using regular maximum
If you're using regular maximum likelihood, yes, you can. We're using residual maximum likelihood, so no, we can't. But we don't need to. It tells us this right here. And that fixed linear time slope explained 21% of the level 1 variance. So in terms of an effect size, I can talk about the reduction in the specific variance component that a given fixed slope is targeting. Because time is a time-varying predictor, it should target level 1 residual variance. And so, in fact, it does. That caused our intercept variance to go up, though. And that is a consequence of how it's estimated and not something to be concerned about. Then we did random linear, right? Did we get through random linear? I feel like not quite. Maybe we did. If we're not sure, then the answer is no. So I'll adopt a term from the other class. Let's re-go over it. Re-go over means present again as opposed to just review. So the new term then that separates this from the previous model, changing from just fixed linear time random intercept now up to random linear time, is our friend U1 here. So U1 is the idea that we are bringing into the model a variable that allows each person to have their own deviation from the fixed time slope. So U1 represents the idea that a slope is a variable and not a constant. So time then, as our continuous predictor, goes in the model for the fixed effects and for the random effects. So it shows up in those 2 places for stata as well, and it shows up in 2 places for R. So time goes in both places. That's not redundant. Outside of the parentheses is the fixed effect. Inside of the parentheses is the random effect. And I'm asking for a likelihood ratio test then, by which to assess whether or not that random linear time slope variance helps the model. So now our R matrix has less variance in it, and the assumption that we're making about dependency and sources of individual differences has changed. How many sources of individual differences does this model say we have? 2, right here and right here. The G matrix. G matrix is level 2. The G matrix is where the random effect variances and covariances live. So this model says people start out differently. How different? 253,258 different. And then the other one is, if I were to say it in as plain English as possible, what idea does that number represent? 2, 2 in the G matrix. Go for it.
So I'm actually curious if this is right. Is it the mean deviations of slope values per person?
It's each person's slope deviation from the mean slope.
But it's not like an average of all those together.
If I took the square root of that number, you could think of it as a standard deviation of how far off a slope is on average. Like each person's slope is from the average slope, yeah. Yeah, this number is people need their own slopes. How much do they need it? This much. And we can test whether these numbers are different than 0, but that's why having the additional measures of effect size can help to put it into terms that people would recognize. Like, what is the expected offness of any one person's slope from the mean? Standard deviation of that thing.
So is that a variance term?
Mm-hmm.
Okay.
Yeah, it is. This is the variance of the U1s across people.
It is clicked.
Okay.
Because I was calling
Good.
it mean
I like
for
the
a while.
click. Yeah, no, it's a discrepancy from the mean. So this is a variance. If I take the square root of it, it's a standard deviation. So that would tell me on average how far off any one person's slope is from the mean slope. The mean slope is the fixed slope. That's why we always have to have both, because the middle is the fixed, and what it's deviating from is the fixed. The random adds that additional component around it. It makes the slope a variable, not a constant. And this number right here, our random intercept variance and its covariance with the slope, those are both at times 0 now, because we've added to the random side of the model. So let me get out a spreadsheet, because I know I'm going to want to make one of these. I always do. So if I have fixed side, random side, okay? If I start out with just an intercept on both sides, what do I call that model? If I have a fixed intercept and I have a random intercept variance.
Random intercept model.
Yeah, people would call that an empty model. Empty means random intercept model is what I call it to differentiate. Unconditional means model. Are either of these conditional on time 0?
Oh.
No, because time's not in there. Now, what if I add a linear effect of time? Then which of these two intercepts is conditional on time 0? Fixed or random or both?
Fixed.
Just fixed. So the conditionality happens on one side of the model at a time. So if I add linear time, the fixed intercept becomes the expected intercept at time 0, given the line that I've just created. Random intercept is still person mean differences, because only having a fixed effect of time means everybody changes the same. So people aren't spreading themselves out. They would be just as far apart from each other at the beginning as at the middle as at the end. Now, if I take my linear slope here and add it, what is now conditional on this side? So this is, I would call, a random linear time slope model. The difference is right here. The intercept, because I have the random linear time slope, the random intercept is now at time 0, too. So everything you learned about what an intercept means is still true. There's just 2 of them to keep track of. Fixed intercept is conditional on what other fixed slopes are in the model. Random intercept is conditional on whatever random slopes are in the model. And likewise, random trumps fixed. So the only way that I could have a random linear time slope and have it work and make sense is that I also have a fixed linear time slope. So that's why I can just call this model, no. Can I just type? Thank you. Random linear slope model. Like, I don't need to say fixed slope, random slope, because that's implied. So linear slope. Same reason, this model, people would call it just a random intercept only, except because it's implied that you have the fixed intercept to go with it. What would I call this model? Wrong. Novice mistake, I would call this model, because this linear random time slope is phrased as a deviation from the fixed slope. If the fixed slope isn't there, it's deviating from exactly 0. And that probably is going to cause estimation problems. It's certainly going to cause interpretation problems. So even if the linear slope is non-significant, it stays if we need the random slope to go with it. So if I had just this, what would I call this version?
Fixed linear random intercept?
Yeah, I'd call it fixed linear random intercept because the sides don't match. And so I give a specific name to each side. Now we're going to add to our pile in just a minute here. So I'll put that away. To be continued. So the V matrix then that is predicted by this model has variances that change on the diagonal, and how they change is given by this formula right here. So a random linear time model predicts the variance to change as a function of time squared. A parabola, a happy face U, that one. Likewise, the covariance is a function of the random intercept variance that we had before, plus a function of the covariance between the intercept and slope and the slope variance, and it depends on which two occasions that we're talking about. So the covariance is predicted to change in a specific way as well. That depends on which two occasions you're talking about. So then the model for the variance has 4 terms in it altogether. 3 of them are in G: random intercept variance, random linear time slope variance, covariance between the two. And then in R, it's just one variance that we're assuming is constant. So E variance is independent and constant after we control for person differences in intercept and time slope. That's what we're saying. This likelihood ratio test right here is not helpful to us. The one that you get by default. Note the degrees of freedom, 3. What it's testing is whether we need the whole G matrix or not. So it's testing the intercept variance, the slope variance, and its covariance all together, which to me is not super helpful. I like to break it into chunks. So we have to do our own likelihood ratio test. So I had included that in the code in SAS with a little macro program that I wrote to do it. In Stata, you can do it with the LR test function, which you first store the estimates from each model and then you put them in here. And in R, it's the Renova function. And they all, fortunately in this case, agree. So 2 degrees of freedom then in comparison to the fixed linear time model, because we've added not just the linear slope variance, but its covariance with the intercept. And a deviance difference, minus 2 log likelihood difference of 43 means, yep, we need it. Here are some effect sizes. So because we have a random intercept around the fixed intercept, we can make an effect size. Because we have a random linear time slope around the fixed linear time slope, we can make an effect size. So it's the fixed effect plus 1.96, so that's for a 95% confidence interval, assuming infinite degrees of freedom. You could switch that out to be another one if you wanted to, but people typically don't bother. And then what goes in here is the standard deviation of the variance term that goes with it. So if I plug those numbers in, the 253 here, that's my random intercept variance. The 1900 is milliseconds. Likewise, the minus 52, that's my fixed linear time slope. And the 2000 number here, that is my random linear time slope variance. So on the whole, I could say that the size of my intercept variance means that at time 0, which is session 1, people are expected to range from about 900 milliseconds to do this task all the way up to 3000. So some people are much faster than others just out of the gate. And then the slopes, minus 145 to 42. So is this a problem that it overlaps 0? No. What this means is that some people are predicted to not change. On average, people are going down by 52 milliseconds a session. Individual differences around that predicts a range from minus 145, so some people are improving faster, all the way up to 42, which is a positive number, meaning some people are actually getting worse. I suspect they're not trying. But if you look at the growth curves for the individuals, just literally the observed data, yeah, some people are getting worse. Not everybody, just this guy. But I'm not going to throw his data away because I don't know what makes this person different from anyone else. Now we get to do quadratics, which is the new piece. So any questions before we do the new piece? I know there's a lot of vocabulary to keep track of, and that's why I keep repeating things over and over, is because it has to eventually sink in. Yes?
Is there a way to test the significance of the confidence intervals of the ranges?
Like, why would you want to know the significance of the ranges?
That's a good question. Well, if you wanted to see if, I guess this would come after you made sure that the level 2 estimates are significant, right?
Yeah, so
Okay.
the answer is yes, in the sense that I can tell you thumbs up or thumbs down whether there is a range,
Mm-hmm.
because that is, does that fixed effect need a random effect to go with it?
Mm-hmm.
But in terms of the size of the range, I would think of this as more effect size.
Okay.
So if you have a ginormous data set and you're going to find everything needs a random slope, but I would come to a very different conclusion about how I would talk about it if I found my confidence interval was like -54 to -50 or something, right? Like tiny. Like it's significant, but yeah, basically everybody's kind of doing the same thing.
Okay.
So I just view this as supplemental information for how you would talk about the slope. Like most people are going down, but the people that are sort of at the highest of the distribution would be actually increasing a little bit. So, yeah. I don't have words for this idea, but
So this isn't talking about the population, this is talking about the sample.
I hesitate to say anything about the population, like in this circumstance or any, but yes. I think of this as like this is describing the sample, assuming that the random effects are normally distributed like they're supposed to.
Mm-hmm.
It's just a prediction meant to convey relative size of information, because people usually don't know what to do with variance, and I'm one of them. Like if you just said my variance is 2,000, I'd be like, good for you. Like I don't know what to do with that. So this helps people to like put it into something they can understand. Okay. Then let me head back to this one. Let's talk about quadratics. So how many of you have seen polynomial effects for fixed effects of any kind, like in regression? You seen it before?
We
Ish.
covered a little bit in GLM, I think.
Yeah, a little bit. So this is one of those things that, like, once you actually learn how to do it, it's much easier. It looks worse than it is. So I would say still the most common way that people introduce nonlinearity of a predictor variable is by polynomial terms. It's easy, it's fast, every software package can do it. So we've started with linear, which is a constant amount of change. If we enter into the model time squared as another level 1 predictor, then that introduces the term for that fixed effect would be a fixed quadratic slope. The slope of time squared is called a quadratic slope. And what that implies is a change in that linear rate of change. The slope itself speeds up or slows down. That's the idea. So a leveling off or an acceleration. Cubic models I have fit one time in my life and had it make sense once, but just in case that happens to you, a cubic model, which would be time to the 3rd power as an additional predictor, that would imply a change in the rate of change of the rate of change, 3rd order. So the extent to which your slope slows down changes over time, maybe. So it's going up maybe, but it's leveling off. And I fit a model once where it was going up, leveling off, but then it started back up again. So that required a cubic to fit the leveling off and then the change in the trajectory after that point. The main thing about this is that all of these terms, if you put them in the model, work together at every occasion. It's not correct to think about like, this is the linear part and then this is the quadratic part. It doesn't work that way. They all work together to create one smooth function. In terms of the number of these that you can have, it is number of occasions minus 1 time slopes that you are allowed. So if you have just 2 occasions, you can have linear time and that's it, because there's one difference. If you have 3 occasions, then you can have time and time squared. If you have 4 occasions, then you can go up to time cubed. And you know why it's the -1?
Intercept.
Yeah, the intercept. We already have an intercept. So if you fit the full amount, that's saturated means. If I have 3 occasions, and I fit a fixed intercept, fixed effective time to the first power, fixed effective time to the second power, that's 3 fixed effects for my 3 means. That is saturated means. It's just another parameterization of saturated means. It's a rearrangement, but you will fit the same, you'll get the same predictions, it's the same. So there's not really a savings there. You may as well just fit this difference and that difference. 4 occasions, same thing. Fixed intercept, fixed linear, fixed quadratic, fixed cubic, that's your 4. That's saturated means. And yes, you can keep going. Like if you had 8 occasions, you could fit up to a 7th order polynomial. Good luck with that. I couldn't tell you what the change of the change of the change of the change of the change means, but maybe somebody else can. I point out that this n-1 rule is for balanced data. It can be broken in unbalanced data. So the difference would be how many separate means are your fixed effects trying to recreate? So in one case, like if everybody comes at the same 4 times, there's only 4 means. But what if a few people come at time 2.5 instead? Well, then you would have 5 means. And if a few people come at time 1.5 instead, then you have 6. So eventually, like if you have a lot of different points on this line, you can fit a higher order polynomial than what any one person's data can provide. But that is presupposing that you can kind of overlay everybody onto the same trajectory, which is a testable assumption. So I would be cautious in trying to fit too much. The pattern of the means that you're starting with should inform you as to sort of how high up you might need to go. And of course, everything is an empirical question as to whether we add it to the model and it makes it better or not. So the rule then, what do we do with this quadratic? Multiply it by 2. That's it. That's the rule. If you can remember that, you're home free. The way that a quadratic slope, so the way that the slope for time squared operates on the linear slope, is that it changes it by twice the quadratic per unit time. So I can give you 3 reasons as to explain why it is this way. The first is borrowing from calculus, because what we're actually talking about is the first and second derivatives of a smooth function. So let's say that I have this model for change, in which the outcome at a particular time starts off with a fixed intercept of 50, a linear time slope, so capital T for time of 4, and a quadratic time slope of 0.3. If I want to talk about the rate of change at any point, then I take time down, take the first derivative of the function, time goes away here, the 2 comes down, and then the rate of change is twice the quadratic. If I take the second derivative with respect to time, then it's a constant number. So 0.6 in this equation is how the rate of change changes per unit time, twice the quadratic. For those of us for whom calculus was a very long time ago or never happened, I got you. Let me explain it a different way. Rules of interactions. So in terms of interpreting an interaction coefficient in a regression type model, if you have, say, an interaction between predictor X and predictor Z, the interaction slope you can talk about as how the slope of X changes as a function of Z, or equally correct, you can talk about it as how the slope of Z changes as a function of X. The interaction does 2 different things at the same time. So that's highlighted here in this first equation here, which is just an example equation from just a regular general linear model with an interaction term. How I would get the slope of X starts out with what it is for X by itself, and then what the interaction term does. So the rules for this are find all the terms in here that have the slope in question, bring them down, and factor out the variable the slope is for. So beta 1 plus beta 3z is how this model tells us what the slope of X would be for any level of z. Likewise, beta 2 plus beta 3x tells us what the slope of z would be for any x. Well, if I put that same logic into our model, I've got time squared, but I don't have the other main effect that would go here. I don't have an analog to the z part. So in thinking about what the interaction term has to do, it has to do whatever it was going to do twice to the one term that it has. So the slope at any occasion starts off with whatever it is at time 0, and then it's twice the quadratic slope times time. And the third rule, if neither of those is satisfactory to you, is just going to be because I said so. That's just the way it is, which I hesitate to bring out as a reason, but if the first two don't convince you, then that's all I got. Why do I have to do it this way? Because I said so. Don't ask questions. That's the mommy side of me coming out. Why do I have to eat breakfast? Because we eat breakfast every day at 7:30. Why? I'm not hungry. Okay. He sits down, starts scarfing his food. That's why. Because you can't tell if you're hungry when you're glued to your Nintendo is the answer. But that's a longer conversation. So, because we're talking about derivatives, because we're talking about interaction terms, or because I said so, multiply your quadratic slope by 2. That's the rule. So here are some practices. So this is stolen straight out of the textbook. I have 4 functions here that vary in their sign of what the linear slope for time is and what the quadratic slope is for time squared. So I have then 0 as the start of the x-axis for time in each of these pictures. And I have then a linear slope of positive 4 in the top corner here. That is the slope of this little line that's meant to be the line that's tangent to the curve to the best of my PowerPoint ability. That's what this is supposed to be. So at this point, for every increase in time, y goes up by 4. The linear time slope is paired with the quadratic time slope of positive 0.3. And so for every unit time, the slope is going to speed up by twice the quadratic. So 1 unit in time later, the slope is now 4.6. 2 units in time later, it's 5.2, and so on. So when the signs match, they work together to speed something up. So I would call this accelerating positive because the slope is going up and it's going more up as time goes on. So this might be something like growth of bacteria on a sponge in your sink over time, right? Some kind of exponential growth. COVID rates at various points in the last few years starting to accelerate. The idea is that the slope is speeding up. And so in talking about the slope, we have to be more specific. Which one? Because the slope at the beginning is 4. The slope in the middle is 5.8. The slope at the end is 7. The model is only going to give us the linear slope at time 0 as a fixed effect, but we can figure out what it would be at any other point in time and ask for a significance test for those slopes too. It's all a function. All right, with me so far? Roomers, are you with me? Zoomers, are we still here? Oh, thumbs right away. That's what I like to see. Thank you. And I once had someone who majored in physics argue with me about my use of these terms, and I said, fine. Like, I'm just going for heuristics. The slope is going up, and it's going more up over time. Whatever words you want to use to convey that is fine with me, because in these models, pictures are everything. So in contrast, if we move over to the right cell, it starts out at the same place, positive slope of 4 at time 0. But now this function was created with a negative quadratic time slope of 0.3. So now the slope that was going up is starting to slow down. So the way that I would talk about it is the slope at time 0 is 4. It becomes less positive by twice the quadratic for every unit time. Less positive, because they're still going up. They're going up less. Going up less is not the same thing as going down. So diminished growth, that kind of idea. So this function then, if we follow it long enough, the slope slows down by twice the quadratic, so slows down by 0.6, positive minus 0.6. What does this model predict is going to happen if we keep going?
Will decrease.
Yeah, it's going to flip over and come back down the other side. Now, math don't care. Math is fine with that. Theory might care. Because let's say that we're looking at like achievement in young children, and the rate at which they grow in their achievement levels off. This model would say that if you follow them long enough, they're going to get worse and forget everything they learned. I know. That is dissatisfying. So for that reason, you will see people be like, quadratic is stupid. Like, it kind of is. It works in a limited time frame. It may do a good job of describing the data you have, but in terms of like theoretically what the model says, that often doesn't match what would actually happen. So it's a valid criticism that it's an oversimplification, because it is. It predicts it's going to come back down. So this would be like the left-hand side of the unhappy U version of the quadratic. Is it a different word besides parabola if it goes up versus down? Okay, so I can say happy parabola versus sad parabola. Can I do that? Okay, so this is the left-hand side of sad parabola. And this one is the right-hand side of happy parabola. Ready for the bottom ones? So this is the left-hand side of happy parabola. This is a negative linear slope paired with a positive quadratic slope. And what I would say is that now the rate of decline is slowing down. Go down less over time. So it starts out at -4. It becomes less negative by 0.6, twice the quadratic at each subsequent occasion. And what does this model predict is going to happen if we keep going? Come back up. So people are getting worse. They stop getting worse and they eventually start getting better? I don't know anything that works like that, except maybe illness, recovery of illness, something like that maybe. That could work. And then the last one, a negative linear slope paired with a negative quadratic slope goes down more over time. This is a decline that is accelerating, is what I would call it. It is the right-hand side of the sad U. Question?
Is this related at all to the autoregressive covariance structures?
No.
Because that had a polynomial, or like the, whatchamacallit?
Yes.
Yes.
Autoregressive was a pattern of covariance in which occasions 1 unit apart were r, 2 units apart were r squared, 3 units were r cubed. So in the sense that you're talking about things that happen with squares and cubes, yes, but otherwise no.
Okay.
Now, how many of you had interactions from me at some point in your life? A few of you. Does this sound familiar? More positive, less positive, more negative, less negative? Not a coincidence, because times squared is an interaction term. Same.
Interaction with itself?
Yes, it's an interaction with itself. So that's why I have to say, instead of this is the change in the slope of x per unit z, it's this is the change in the slope of time per unit time, because it's with itself. But there's only 4 kinds of quadratic trends in the same way that there's only 4 kinds of interactions. It takes a slope and either makes it more positive, more negative, or less negative. That's it. So which linear slope you get depends on what? How am I going to know which of these numbers shows up in my output as the slope coefficient for linear time?
Which time you are interested in?
How do I know which, like so in each of these pictures, like I have 6 different slopes. How do I know which of these numbers is going to show up on my output that goes with the slope of linear time? Which one am I going to get?
4.
Hmm?
4.
4? Why am I going to get 4?
those the linear parts.
Keep talking. You're right. I am going to get 4. I'm going to get 4 in all the pictures because
That's the fixed linear.
it's the 4 is going to be the slope of the fixed linear time. But why do I get 4 as opposed to 7 or -1 or whatever else?
Because we have time 0.
Time 0. Yes, that's why. The linear slope you get on your output is the time 0 version. The model tells you what it would be at any other time, though. And we will write statements, estimate statements, to get the slope at any other time, in the same way that you can get a simple slope out of an interaction term at any level of the moderator. Not different. All right. Okay, back to Excel for a minute. So conditionality, right? Come on. Trying to make it bigger. I think this is as big as it gets. Okay, well, can I make it bold? There. So if I add to my pile here, if I add a quadratic slope, I have added a fixed effective time squared. What do you think is going to happen to the interpretation of my linear slope?
Time 0.
At time 0. What about my intercept? Is that going to change? It's still at time 0, but what the number is for it is going to change because it's expected at time 0 based on a bendy line instead of a straight line. Different expectation. What would I call this model, do you think? This combination right here.
Fixed quadratic random linear.
I would. I'd call it fixed quadratic random linear time because it doesn't match. Could I do that? Could. It's coming. If I did that, what changes in terms of conditionality? Anything on this side? Nope. Anything on this side? What's going to happen?
There's going to be a quadratic.
Both random intercept and linear random component will be centered at time 0.
That's it. They're both at time 0 now because we have this conditioning on it. So the highest order term is unconditional. Lower order terms become conditional on the higher order term. So once we have quadratic on both sides, the fixed quadratic makes the fixed linear conditional at time 0. Random quadratic makes random linear conditional at time 0 also. What if I went insane? Could I do that? How many occasions do I need, first off, to do that? 4. Yeah. But it would not be a good idea with 4, but I could do it. So what do you think might happen to the interpretation of our quadratic slope if it's underneath time to the 3rd? It's at time 0. Yep. What if I went really insane? Random cubic model. That guy's now conditional at time 0 too. Yep. So every time you add something, everything underneath it is going to shift around because it's now conditional at a point. You control where that point is because you control where time 0 is. Question or head scratcher?
Kind of. Could you say this in real world, like a real world example? Not for the cubic, but just for the putting quadratic on both sides.
What would it mean?
Yeah.
Okay, let's not go insane. Let's just this is this much. What it would mean is, so I will foreshadow what's going to happen with our data. Our data are going to look like this bottom left picture here. Because people are decreasing in response time over time. What we are about to see, it looks like we're going to see it next week maybe, is that people are the rate of decrease, I would say, is slowing down. So people get better right away, but then the rate at which they get better slows down. This is like pretty typical for learning data. And in this case, more is worse, right? This is response time. So faster is better. Going down is good. But the rate of improvement is going to level off because if you keep doing this over and over again, eventually you're going to not improve anymore. So we're looking at this scenario. So random intercept would say people differ in where they start out at time 0. Random linear would say people differ in their rate of change at time 0. So some people are on a steep trajectory right away, other people are on kind of a flatter trajectory right away. What random quadratic would be is people differ in the rate at which they slow down. And that's probably going to be heavily tied to the intercept for where you start. Because people who suck at this have way more room to improve. People who are doing well to start with can't improve as much, they have to slow down more. So there's going to be correlation among these random effects to describe the same person as a consequence of just how this works. That will usually be the case. Does that help?
Yeah.
Okay. If we do the top right picture as a contrast, so I would say this is a rate of change that's positive but slowing down. If we had a random quadratic model, then let's say kids need their own slopes, but kids also differ in how much they slow down. Something like that? Yeah?
This is a crazy idea, but could you diagnose or like classify people based on how fast?
Yes.
Okay.
So diagnose or classify puts us into the SEM world of what is known as latent class, latent profile, latent stuff. Profile, maybe? There's also mixture models, which is latent class on top of a growth model. But those are really usually kind of silly because the classification is on top of the random effects, in which case it limits the kinds of change you can have. But yeah, in theory, you could have the extent to which someone slows down, that random effect, as a predictor of other stuff. So you can do anything you want if you can figure out a way to model it. That will always be the answer to that question.
That sounds fun.
It is fun. I'm glad you think so. Data permitting, of course. But yeah, the key idea is that in these models, we're using 3 things to describe the trajectory. A starting point, because we've centered time 0 at the beginning. A linear slope, which becomes the initial rate of change. And then a change to that rate of change, which is the quadratic. If you have enough occasions, you can have a random effect on all 3. People can differ where they start, they can differ in their initial rates of improvement, and they can differ in the extent to which they slow down or speed up. Yep. Data permitting is the key word here. Do you want to see, let's see. I don't know what we're going to see. Let me see what I else need to say about this. So words that go with the Excel sheet on what's conditional on what. I already said that. The idea that each of these can be random. So the constraint on random quadratic is n-2. So in terms of the number of slopes per time that can be random, it's n-2 for the number of occasions. The 2 is because we already have a residual variance and a random intercept variance. So here's what the notation would look like, very briefly. Red is fixed, blue is random. So if I had a random quadratic model, I would need 3 beta placeholders. Each person gets an individual intercept, individual linear time slope, individual quadratic time slope. That's what I would name each of these 3 betas. So then we have a corresponding demarcation for each of these. Fixed is the middle. U is how far off yours is. So beta 0, because we're predicting the intercept, both of these terms start with 0 in the first subscript. Because we're predicting the linear slope in the second equation, both of the terms start with a 1 in the first subscript. And both start with a 2 in the third equation. So the fixed part is what happens on average. The random part is the deviation for U, for which we have a variance. So how many different kinds of between-person differences are in this model? How many kinds of between-person differences? 3. So that gives each person-level predictor 3 different things it could do. So why do you think that some of these older adults differed from each other in their ability to do this task? What's an obvious answer?
Age?
Age. right? Let's be discriminatory and say that, 80-year-olds can't do it, but 65-year-olds can, or some stuff like that. So if I threw age in here, that's what I was going for, by the way. I'm not mocking you. That's the first thing that people would put into this model because it would be viewed as a control. So if I put age in here, I'm saying age is one reason why some people start out slower than others. If I put age in this little equation in the middle, age is one reason why some people initially improve less fast than others, and age might be a reason why some people decelerate more than others, slow down more than others. 3 different ways that people differ from each other, 3 different roles that person variables can play as predictors. For those of you in the SEM class, if I have 3 betas, how many latent variables would have to go into my structural equation model to match? 3. Yeah, 1 latent factor for each beta. This one would have loadings fixed to 1, this one would have loadings fixed to time, this one would have loadings fixed to time squared. Yep. Yeah. It's all the same. The mean of the latent variable is the fixed effect. The latent variable itself has a variance that would be the variance of each of the random effects that go with it. Yep. All right. 143, I think that's a good enough for today. How about you? Yes, indeed. All right, any questions before we call it a week? Not a day, but a week.
What's the highest order that you've seen published, in terms of the...
I'd say cubic. And at that point, they don't even try to interpret it. They're like, just look at my picture. It's cubic. But there are rules for that too, and you can read about them in Chapter 6 as to what to do with cubics. All right, then no office hours tomorrow, no class Thursday. I will see you in here next week. Have good things happen to you. Have good weekends. Have good Thursdays. Thank you for being here. Let me know if you need anything.